Hello everyone, I'm Daniel Gratzer. Today I'm going to present some joint work between myself, Kavvos, Andreas Nuyts, and Lars Birkedal. So that's work on multimodal dependent type theory. To begin with, the question that we're interested in is taking type theory and applying it to new situations. And these situations might be on the more computer science side, or they might be on the more mathematics side. So for example, I'm interested in staged programming, which might be useful for designing a macro system for dependent type theory. Also proof irrelevance, guarded recursion, and parametricity. But more than this, I'm interested in using type theory to study things like realizability, abstract notions of topology, or geometry. And so each of these situations, in order to make type theory more useful, I'd like to add some new features to type theory. This is most apparent on the computer science side. I'd like features which allow me to model guarded recursion, parametricity directly. And so one might hope we can just add features that sort of take care of these things for us. But if we do, we're going to disrupt the properties of Martin-Love type theory that make it useful. In particular, we'll lose substitution. And without substitution, every single property of type theory comes crumbling down. So we can't just naively add features. So in each of these examples, what we can do instead is add these features in such a way that they're guarded by a modality. And the modality is going to manage the interaction between new operations and the old type theory so that substitution is preserved, but moreover, canonicity and decidability of type checking can also be preserved. At this point, I think I need to define what a modality is because it's a term which is used in a variety of contexts. Some people use it in the sort of maximally general way. A modality is any unary type constructor. And this encompasses all possible modes of use, but it's a little bit too general. There's very little that I can say about all modalities if a modality is a unary type constructor with no additional structure. Some people use it to mean the more restrictive thing of an internal functor of some sort, or even a monad. For our point of view, we're going to be interested in modalities which are right adjoints. And this is not a right adjoint in an internal sense, but a right adjoint on some appropriate syntactic category is a good intuition. And this restriction is justified in two ways. First, as we'll see, it gives a practical syntax for programming with modalities. And it also includes all of the examples that we're interested in. Now, with that said, let me tell a story about the current development of modal type theories. This is sort of like, I think, a representative example of how things are currently done. So in around 2017, work on guarded recursion started to converge towards a particular style of presenting modalities, the Fitch-style. And so this happened in two independent works. And then this was isolated into a sort of core type theory by Birkedal et al. And this gives a dependent type theory which doesn't explicitly mention guarded recursion, but uses the same style, the Fitch-style, to present the modality. Then later on, myself and collaborators took this system and tweaked it a bit so that the modality has some different properties, and we then proved normalization for our system. Now, each of these type theories is related to each other, both historically and also practically. The judgmental structure between all of these is very, very similar. But this relationship is informal at best, and I can't reuse any of the proofs from these type theories. And that's unfortunate, because a normalization result is a substantial amount of work, and I would like to port it to the core type theory from Birkedal et al. And so now I can talk about our core contribution, which is the dependent type theory, MTT. So MTT is a modal type theory, but it's not a modal type theory for a particular modality or even a particular collection of modalities. Instead, it's a full type theory parameterized by modalities. So a user can instantiate Martin-Love type theory with a collection of different modalities, and MTT will then give you a system where you can manipulate these modalities in a safe way. And we have proved results such as canonicity that hold irrespective of the choice of modalities. So we've applied MTT to several different situations, including axiomatic cohesion, a form of abstract topology, guarded recursion, parametricity, and several others. So let's talk a little bit about the story that I told 2 slides ago. So we had a core type theory for Fitch-style modalities, and then an extension of that type theory. And more precisely, Birkedal et al. Added a single modality, box, and a form of the K axiom, which is a sort of product preservation or functoriality condition. And I'll note that this all takes place in dependent type theory, so there's actually a dependent version of this operation, which I chose not to write out. Now, this is already quite substantial, and the work that my collaborators and I did, we added 2 more operations to the modality, which made it into a comonad. And we did this in a very sort of systematic way. We tweaked the behavior of the judgments so that these operations fell out naturally. Now, we can't reuse anything from the this type theory currently, but using MTT, we can actually get some reuse. In particular, if we were to use MTT to solve this problem, we wouldn't design 2 separate type theories. What we would do is we would take MTT and instantiate it twice to yield type theories comparable to this pair of type theories, and prove normalization for MTT irrespective of the mode theory, and then obtain a normalization result for both of these. So MTT is making this superficial similarity between type theories into a formal relationship. Now, before we go further, I should say MTT is not just a type theory with multiple modalities. It's in fact a type theory with multiple modes. And so a mode is sort of like an independent copy of type theory. So MTT comprises of several different modes, each of which has its own pi, its own sigma, and modalities bridge between these independent type theories, allowing us to use types from one mode in another. And this arises already in many sort of natural situations. So if we're using axiomatic cohesion or spatial type theory, we have 2 sorts of universes of things. We have the types which are discrete, those are modeled by sets, and then the types which have continuous behavior that are modeled by spaces. And we can think of this as having 2 separate modes. And now we can follow the work of Licata-Shulman, which extends Reed 2009, and specify our mode theory systematically as a type of 2 category. And so the correspondence here is that an object corresponds to a mode, a morphism to a modality, and a 2-cell becomes a relationship between modalities. I'll use the term coercion. And it basically means that there is a natural map between these modalities. So I think it's nice to see how this might work in practice. So let's look at a sort of simple mode theory for a second. So it'll be generated by the following data. So we have one mode, M, and one generating modality, mu. And that generating modality is going to have a copoint, so a way of extracting from mu to 1. And we'll further impose some equations here. We'll say that mu mu is always mu, and that any pair of 2 cells are equal. And if we feed this mode theory into MTT, we end up with a single modality for the generating 1 cell, along with a pair of coercions. So one coercion comes from this 2-cell, and that's extract. So it says if we have a modal type, we can extract it. And this equation results in a different coercion, which allows us to duplicate the modality. And in fact, the fact that this is an equality will mean that this is an equivalence. And these operations will satisfy the comonad laws, so we can sort of obtain an idempotent comonad in type theory uniformly from MTT. Now, as a bit of notation here, you'll notice that all of these judgments have these M's at the end. And this is a mode annotation. It tells us what mode this judgment is taking place at. For the present example, there's only one mode, so it's perhaps not the most interesting piece of data. But as we go further, there'll be multiple modes, and then it will be important to keep track of where each judgment takes place. So we now need to be a bit more formal. Let's fix a 2-category M, and that will be our mode theory throughout. So MTT is going to have the standard judgments of type theory localized to each mode. So there'll be a judgment saying gamma is a context at mode M, A is a type at mode M is a term at mode M. And each of these judgments is going to contain a copy of MLTT. So there'll be rules for sigma, pi, a universe, and an intentional identity type at each mode. But the more interesting bit is the part which is not strictly corresponding to an LTT, and that's the modalities. So the idea is that a modality acts like a functor between modes. So given a closed type at mode n, and a modality mu going from n to m, we'd like to end up with a closed type at n. And so this sort of suggests the following rule, which says that if we have A, then we get mu A. The issue is that this doesn't scale to open types. Open types take place in a context, and now we have to ask what mode this context lives at. Up here, we needed to live at mode n, and down here, we needed to live at mode m, and a context lives at exactly one mode, so somehow we have a clash here. This is perhaps not the most surprising problem for those familiar with modal type theory. We're going to need some additional judgmental structure in order to make this make sense. So in particular, we're going to follow the Fitch-style. So the Fitch-style adds an operation to context, which we write loc sub mu. So we'll get one of these for each modality. And the idea is that loc mu pushes gamma backwards along mu. So intuitively, you should think of loc mu as being the left adjoint to the mu modal type. However, this is best kept as an informal intuition, because this acts on contexts and this acts on types. So it's not even clear what categories would be in scope here, but it's good to sort of keep that in the back of your mind. Now, this intuition immediately pays some dividends because it tells us how to write down the introduction and formation rules. So I have the introduction rule here. And the idea is that it's just transposition. We have a mu type here, and we transpose to get a locked context above the line. So this tells us how to introduce a mu modal type. And for those familiar with the literature, this follows the Fitch-style approach to modalities, which is also where we inherit the lock notation from. Now, one difference from previous work on Fitch-style type theories is that MTT has multiple modalities, and then that tells us that there'll be multiple locks. So we have to figure out how these locks interact. And luckily, there's a systematic sort of answer to this, which is we'll force locks to behave like a sort of two-functor. So we'll impose a definitional equation on context, which says that locking at one is the identity, and that locking twice is the same as locking at the composite. In fact, lock is going to be formally part of a two-functor from the mode theory, and the action on two cells will give us the following admissible rule, which is a form of lock weakening, if you like. It says that if we have two locks, which both go from n to m, if we have a term which is locked at nu, we can weaken it to a term locked at mu, provided that there's a two-cell going from mu to nu. But I'd like to draw attention to the fact that this is a dependent type theory, and therefore it's not sufficient to apply the annotation to just m here. We need more than just m superscript alpha. We also need to superscript the type with alpha, because the type also lives in a context locked at nu and must be adjusted to live in a context locked at mu. Now, in the process of adding locks to our context, we've actually created a new problem, which is what's going on with the variable rule. Previously, the variable rule in type theory just says you can grab a variable from anywhere in the context and use it. But now that we have locks, does it really make sense to grab a variable from behind a lock? After all, look at this example here with a single modality and a single item in a context. Here, we seem to be expecting A to live at mode n, and over here, it's supposed to live in mode n. And this is sort of mirroring the issue we had with context before. A can't really live at any given mode, so that's a problem. Now here we're going to diverge from Fitch-style type theories with MTT. Previous Fitch-style type theories had an elimination rule for modalities, which was the other direction for transposition, and that allowed us to remove locks from context and thereby access variables behind them. In MTT, we're going to do something different. Instead, we're going to annotate variables in the context, not just with their type, but also with a modal annotation. So this is not X being a modal type of A formally. This is a piece of judgmental structure. Now, intuitively, X annotated with mu is the same as X being a mu modal type, but formally they're distinct. And this distinction is going to allow us to sort of bridge the gap and write down a coherent variable rule. So that's this. And really what it says is variables are determined by the co-unit of this adjunction. I think a more helpful intuition is that if you have a mu annotation, it precisely cancels a mu lock. And bridging the gap up here is the domain of the elimination rule. So the elimination rule is a pattern matching rule which allows us to shift from some mu modal term to a mu annotated variable. Now, the variable rule from the previous slide is a little bit too restrictive because it requires the annotation and the lock to match on the nose. And our mode theories have a richer structure that allows us to have a slightly more flexible rule. So if you can see here, we don't require them to match exactly. We only require them to match up to a 2-cell. And so here we access X with the 2-cell alpha. And the alpha tells us how to bridge the gap here. And in fact, in the semantics, this is just a combination of the co-unit rule and then the action of lock on 2 cells. So this is a good time to step back for a moment because I think it's really easy to feel like this is just one damn rule after another. And we sort of lose track of why we were doing any of this in the first place. So our high-level goals were to get a modality for each morphism in the mode theory and a coercion for each 2-cell. And so we sort of started by trying to write down the introduction rules and discovered that we needed a richer context structure, which led us to adding locks, and then we had to factor locks into the variable rule. And this created a new problem, so we added annotations to our context and then started annotating occurrences of variables with 2 cells. Now there's, of course, a distinction between an annotated variable and a variable of modal type, and the modal elimination rule bridges the gap. So each of these things is serving one of these 2 goals of getting a modality for each morphism and a coercion for each 2-cell. Now the fun bit is that after we do all of this, the mode theory is sort of reflected into the term language of MTT, independent of the particular mode theory. So we always end up with some sort of equivalence between the identity modality and the identity. And we're always able to apply a sort of composition rule for modalities. We get a coercion for each 2-cell, and we get a functoriality style rule for each modality. And all of these really follow from the 2 functoriality of lock. The structure of locks is reflected into the structure of modal types. And I should remark that these are the equivalences that one might be familiar with from the Hop book, say. So I think it's a good time to do some actual programming here. So let's see how you can actually write out the term that witnesses these coercions. So say that we have a modality which goes from a 2-cell, which goes from mu to nu. We want a function which goes from mu a to nu a. So we start out, we have in our context X annotated at the identity of type mu a. So let's start by applying the elimination rule, which is going to add a new variable to our context, which is of type A, but now with a mu annotation. At this point, there's nothing really to do on the left, so we'll apply the introduction rule. So that's going to shift our goal to just being A, but at the same time, it adds a lock to our context. So now we have A and A. So we'd like to use Y in this case, but there's a mismatch potentially, mu versus nu. So we use the 2-cell alpha to cancel the annotations and fill in our program. Next, let's look at composition. So again, we start with some X, which is going to be of the composite modal type now with the identity modality. So we'll start by applying the elimination rule. We now have y here, which is annotated with mu nu, and our goal is the composition of two distinct modal types. So we'll apply the introduction rule once and twice. Now we're going to make use of the definitional equality that we imposed on context, which is going to let us collapse those two locks into one. And now we have this canceling with this, and we can pull out that y. So there are two programs, and there are further details on some of the rest of the combinators either in the paper or the attendant technical report. We have proven some results about MTT which hold irrespective of the mode theory. So the first and sort of most basic is that the type theory is consistent no matter what choice of modalities you instantiate it with. There's never going to be a way to prove that true is equal to false. So that's quite handy. But more than that, subject to a small technical restriction explained in the paper, for any closed term, irrespective of the mode theory, we can tell you that that closed term is either true or false if it's of type bool, or if it's a modal type, then every closed modal type is a closed type from a different mode. Every closed term of modal type, I should say. So both of these are explained more fully in the paper, but they hold irrespective of the mode theory, which means that we can sort of get these for free when we instantiate the MTT to a particular situation. So on the subject of particular situations, as a last part of this talk, I'd like to explain how MTT can be useful for something which was already worthy of study. So let's talk about guarded recursion. So here is a one-slide introduction to guarded recursion, which is perhaps a bit optimistic. So the key idea with guarded recursion is to isolate productive and co-inductive programs using types, so specifically modalities. So we have a modality which tags a computation as not really being available right now, but only available to us after we've done some work. So if we have something which is available now, we can always forget that it's available now and use it later. But the key operation is love induction, which says that if you assume that something is available later and produce it now, that's sufficient to get it right now. So this is a sort of inductive principle, which is going to give us guarded recursion. I should say this is like induction on the time step. Now, on its own, later and love just give us a way to have sort of synchronous guarded programs. But we want more than that. So we add a second modality, box, which tags a computation as being independent of the time step. And this forms an idempotent comonad. But box also crucially interacts with later. If something is independent of the time step, then having a later doesn't really give you anything. So we're allowed to get rid of it. So if something is under a box and a later, we can allow the box to consume the later and just get box A. And this operation is what gives us co-induction. So I've just presented the classical formulation of guarded recursion, or one of them, which is a pair of modalities. In MTT, we'll encode guarded recursion not as a pair of modalities, but as a pair of modes. So we'll have two modes, one being types which have no notion of time, so that's sort of like sets, and one being types which do vary over time. So that's kind of like pre-sheaves over omega, or the tuples of trees. So there's a pair of modalities which go between these things. We can take any constant type and forget that it's constant and allow it to trivially vary over time. We can also take a type which does vary over time and restrict our attention to its global elements, so things that are always available. And doing the loop down up is precisely box A from the previous slide. So we can recover the always modality from guarded recursion in this way. The later modality is represented as a sort of loop going from time-varying types to time-varying types. And so these operations give us a handful of modalities, which I've given more convenient notation over here. And in order to get the appropriate equations between these modalities, we add some equations to our mode theory. Now, I've written this with a less than or equal to here because rather than working with a proper 2 category, I'd like to work with a poset enriched category. So the set of two cells between any pair of modalities is subsingleton. And so these equations, together with these one cells, allow us to rederive a lot of the operations from guarded recursion uniformly. These all follow from combinators that we already had in MTT. On the other hand, lob induction isn't really present yet. And in fact, we can't recover lob induction as an operation from the mode theory. So instead, we axiomatize it. In the future, we hope to have a more systematic way of deriving this. But at the present, just axiomatizing lob, we can already reproduce a lot of examples from earlier guarded type theories cleanly inside of MTT. So, thank you for watching this. If you're interested in more information about MTT, there are papers available on my website. So the LICS paper is here, and the accompanying technical report is also there.